Greetings! My name is Dr. Laura Christianson. I'm an assistant professor and extension specialist in the Department of Crop Sciences at the University of Illinois, and today we'll be talking about the why, what, and how of tile drainage nutrient loss. Thank you for choosing to watch this video today. I know this is a little bit of an unusual format for the crop management conferences, but I think it provides us some benefits primarily in that it's keeping us all safe. Another benefit of the video format is that I find that you can rewind and watch these videos. There's a lot packed in the coming 25 to 30 minutes, but you can always rewind, slow it down, and watch parts again if you want to. Just so that we start out on the same page about what we're going to talk about over the next 25 to 30 minutes, the learning objectives are listed here. In short, we're going to increase familiarity with some terminology that has to do with water science. We're going to get a feel for rule of thumb nitrogen concentrations and losses that are kind of normal in tile drainage. And then we're going to understand how we collect tile drainage water samples and how we estimate tile drainage flow rates. Now today, whatever day it is for you that you are watching this video, today we're going to start with the why. Why is monitoring edge of field tile drainage loss important, and why do we do this? I should make clear here that our context for this seminar today is the context of subsurface drainage or tile drainage. In terms of water monitoring, there's a lot of general guidance out there for stream or river sampling, groundwater sampling, water, wastewater sampling, but our context here today very specifically is tile drainage. With that in mind, one of the primary purposes of edge of field tile drainage monitoring is to help assess if our conservation practices are working. In other words, we use edge of field monitoring to determine if the practices that we promote for reducing nutrient loss are working like we think they should. Now, for agronomists or soil scientists, in-field monitoring would include soil sampling, gas sampling, biomass sampling, yield monitoring, and more. For water scientists and engineers and water people, I'll say, edge of field sampling is an assessment of the water that's leaving the field. So you would imagine this is done at the edge of the field, or in some cases at the edge of a plot. Now, that's not to say water people aren't interested in in-field water quality or quantity. We often do use monitoring wells or piezometers like I'm showing here, tensiometers, calibration of irrigation sprinklers in the field. But in this session, in this seminar, we just happen to be focused on edge of field tile drainage nutrient loss. And we're lucky in some ways with tile drainage because we have a pipe to work with. Granted, that pipe is 3 feet underground, but if you are monitoring surface runoff, for example, it's much more difficult because you have to have generally flumes like I'm showing here to help you with the monitoring process. Now that's the why of why edge of field monitoring for tile drainage nutrient loss. Now let's talk a little more specifically about what we are actually looking for when we talk about edge of field tile drainage monitoring. We're going to start with the upper left corner of this table, and this table is going to be our home base for the rest of the presentation. We're going to keep coming back to this table and talk about all 4 corners. We're going to start with nutrient concentrations. Nutrient concentrations are a mass per unit volume. Always when we talk about concentrations in terms of water science, we're always talking about a mass like grams or milligrams or micrograms per volume, and that's always liters. When we talk about nutrient concentrations in water, they're always, always, always in metric. You would never say something like 10 pounds of nitrogen per gallon. That's a concentration, but it's not a concentration that exists anywhere. It's always a mass per volume in metric units, like I'm showing on the screen. One way to think about a milligram per liter is that a grain of sand weighs about 1 milligram. So you take a grain of sand, put it on a scale, and it weighs 1 milligram. If you add that grain of sand to a 1 liter bottle of water or 1 liter bottle of pop, then you have 1 milligram of sand per liter. Again, mass per volume. Concentrations are something that can be measured in the lab. So the benefit here is that you can go to any water body around the state or even your tap in your own house, take a water sample, send it to a water quality lab, and the number that analytical equipment will tell you is a concentration. It's not a mass, it's not pounds, it's always a concentration, milligrams per liter, micrograms per liter. Concentrations are also important for things like numeric criteria. For example, our drinking water standard. For drinking water, we don't want any more than 10 milligrams of nitrate nitrogen per liter. Again, that's milligrams per liter. That's a concentration. And then we use concentration values for toxicity assessments for things like heavy metals in water. This term concentration is also used for a concentration of a substance in the air, or for example, concentration of nutrients in the soil or in our grain. In those contexts, you would use mass per mass, something more like milligram per gram or milligram per kilogram, milligram of nitrogen per maybe kilogram of grain or soil. That's different because that's a mass per mass. For water science, we're always talking about a concentration as mass per volume. And then lastly, you might hear sometimes parts per million used or parts per billion used. For water, 1 milligram per liter or concentration equals 1 part per million. And that just relates to the density of water. Now that we've talked about concentration, what concentrations are, the next natural question is, well, what's a natural or what's a kind of normal rule of thumb nitrate concentration in our tile drainage water? Several years ago, I did a large-scale review of to my knowledge, every published drainage water quality study from North America. We compiled all of the information from all of those studies in a database, and then I had a student add to this just a few years ago. Based on that large-scale analysis, we can make graphs like this showing the range of nitrate nitrogen in tile drainage water samples. You'll see at the bottom of the screen it's a decently large sample size. We had more than 900 observations from these 40 or 50 years of drainage studies, 900 individual nitrate concentrations reported as flow-weighted annual nitrate concentrations. And so this gives us confidence that this is fairly representative across the Midwest, across the Corn Belt, and across many cropping systems, but really primarily for corn and soybeans. What we found was that our mean value, our mean nitrate concentration, and all of those 900 studies from the 40 and 50 years of drainage studies, our mean was about 13 milligrams nitrate nitrogen per liter. And our median value was about 12 milligrams nitrate nitrogen per liter. So if I wanted to get a feel for what's a normal or typical tile drainage concentration for the Midwest, for corn and soybean cropping systems, I would say generally we're talking about 10 to 15 milligrams nitrate nitrogen per liter. And that's based on the mean and median values here. Now I know what you're saying. Hold on, Dr. Laura. I'm doing a cover crop. I'm following 4R's nitrogen management. My nitrate concentration should be a lot less than what you're showing on that graph. And that may be the case, but I just want to give you a general rule of thumb, numbers for your back pocket for what normal values for nitrate concentrations are in our tile drainage across the Midwest. Now let's put this in context of the Illinois nutrient loss reduction strategy. The table that I'm showing at the bottom is from our very own nutrient strategy. It's our recommended nutrient criteria for the state that was developed as a part of our nutrient strategy process. This table isn't a direct apples to apples comparison for what I showed you on the last slide, because this table is shown in total nitrogen, and the last slide was, of course, nitrate nitrogen. They're pretty close, so we're going to use them as an example anyway. And the second difference is that this table is in micrograms per liter rather than milligrams per liter. But that's just a conversion by a factor of 1,000. So for example, the numeric criteria for the North region for the state of Illinois is we want to keep our total nitrogen concentration less than a 3.979 milligrams per liter. This recommended criteria is much lower than the average rule of thumb drainage concentration we talked about on the last slide. My point here is that in tile drained areas where a large portion of the wadeable streams are made up of tile drainage water, it's going to be very challenging to meet these nutrient criterion without getting really serious about conservation practices. Now coming back to our home base, the next square that we're going to fill in is how do we exactly measure nutrient concentrations for tile drainage water. We've talked about what they are, what are typical values, how do we actually measure them. The process of measuring nutrient concentrations in edge-of-field tile drainage monitoring generally involves collecting a water sample. There's two basic ways to do this sampling: by hand, which you see in the picture on the left, or using automated sampling equipment, which you see on the right. The selection of the method, how you collect your samples, obviously depends on the goals of your monitoring. It also depends on your resources, not just money, but also available labor and time and personnel. For a farmer or landowner, you would probably use the manual sampling, the sampling by hand method, rather than using an auto sampler. Now I'm going to show pictures of if you would be sampling from a control structure, which is shown at the bottom of the picture, the little gray box there. We'll talk more about that in a couple minutes, but you could also do this kind of sampling if you had access to a tile outlet. To collect grab samples from tile drainage, first of all, you bring your fancy highfalutin sample collection stick, which doesn't have to be very fancy at all. You see in the picture it's just a PVC pipe with a bottle taped to it. You position the sampling stick to collect water over the flowing stop log if you're collecting a sample out of a control structure, or you would collect your sample from the water flowing out of your outlet. But it's not quite as simple as just collecting a sample. What you want to do is first rinse the bottle on your sample stick about 3 times so that you can be sure everything inside the bottle is actually representative of the water that you're collecting. Now this is important. Even if you were to, say, rinse the bottle out with high purity lab water, you still want to rinse the bottle with the water that you're collecting, because the high purity lab water could potentially dilute the water that you're collecting. So you rinse the container before collecting your sample, you fill the sample bottle, cap it, make sure it's labeled, and then you store it either on ice or frozen, usually on ice for transport, and then you store it frozen until it can be analyzed. Now, if you do have funding for auto samplers, they provide a lot of really excellent flexibility. And note that the pictures I'm showing for this part are generally Teledyne ISCO brand, but I do want to say use of brand name does not necessarily imply an endorsement, because there are a number of brands of auto samplers available for sampling water. Every auto sampler has a couple of basic parts. First and secondly, every auto sampler has programmable electronic operation and memory, like a little computer. And then secondly, every auto sampler has a sample collection pump. The programmable computer of the auto sampler is what controls the pump and tells the pump to kick on to start pulling the water sample up so that the water sample can be put into the bottles. You can have up to 24 either glass or plastic bottles like you see in the picture. Or you can also have a configuration in an auto sampler, which is one large bottle to collect a composite sample. We'll talk about composite samples in a minute. The last thing that auto samplers have are what's called a stage recorder, which is essentially a flow sensor that lives down in the water that you're sampling, but it actually talks with the auto sampler. It's connected to the auto sampler. Why do these stage recorders or flow sensors matter? They allow you to do what is called flow-based samples. There's 2 options for determining a sampling interval if you're using an automated sampler and you don't have to actually physically be there in the field collecting the samples. Time-based samples are where you might collect a sample every 4 hours or maybe every 4 days, and the auto sampler is programmed to do that. Flow-based sampling is where you program the auto sampler to sample rather every 2,000 gallons that's flowed through that tile, or every 20,000 gallons or 20,000 liters that's flowed through that tile. Another aspect of auto samplers is that you can do discrete versus composite samples. Discrete sampling is where you take one sample and put it in one bottle, and that's it for that bottle. It's a snapshot of what's in the water at the time that that sample was collected. Composite sampling increases auto sampler capacity essentially by collecting more than one small water sample into the same bottle before moving to the next bottle, if you have multiple bottles in there. For those of you that do soil sampling, you'll be familiar with this idea of composite sampling, because we often do composite samples for our soil samples in a field. You take a number of small samples and composite them into one to be sent to the lab. Now, an obvious question is, how often should we collect samples? Either if you're grab sampling by hand or if you have an auto sampler. For tile drainage, if you're interested in nitrate, the general rule of thumb is that you want to be collecting a tile drainage water sample at least once a week. If you're interested in dissolved phosphorus, in addition to nitrate, you need to be sampling generally every half a day to day. One last mention for how nutrient concentrations can be measured. Obviously, when you collect a water sample, you need to then send it to a lab and have it analyzed for the nitrogen or the phosphorus or whatever you're interested in. There are some other options though. At the bottom of the screen, you see YSI handheld sondes. You basically stick these sondes into the water body that you're interested in or into a bucket of your tile drainage water that you've collected, and they read out a nitrate concentration. So there is no sample collection involved if you use those sondes, water quality sondes. The challenge with these, though, is that people often don't realize the calibration burden. These sondes have to be calibrated every couple hours if you're using them over the course of like a day. They definitely need to be calibrated every time you go out. What I'm personally a little more excited about are real-time deployable nitrate sensors. Now, these real-time sensors are still very expensive, anywhere from $15,000, which is a bargain, up to about $40,000 a piece. However, these give us the capability to measure continuous nitrate concentrations in a stream or a river or a tile drain in real time. So for example, rather than taking a sample today and going back and taking a sample 2 days from now, I can deploy a sensor like this and have a nitrate concentration every 30 minutes or every 15 minutes between those times. Now again, back to our home base. We've talked about nutrient concentrations in water. We've talked about how we measure those concentrations in water. The second part of edge of field tile drainage monitoring is knowing how much water leaves through the tile. But I'll say what we're really working toward here is being able to estimate nutrient loads and losses, not just knowing how much water leaves the field. The end game is being able to estimate nutrient loss. We need both nutrient concentration and water flow to estimate annual nutrient losses. A little terminology here. A load is simply a mass, like 400 pounds of nitrogen flowed through that tile, or 200 kilograms of nitrogen flowed through that tile. A load is a mass. A loss is actually a normalized load, normalized by area, like 20 pounds of nitrogen per acre, or 20 kilograms of nitrogen per hectare. Loss is sometimes called yield, a yield of water or a yield of nutrients. And that'll sound familiar because we obviously talk about grain in terms of yield, and that yield is area normalized, bushels per acre. And the term loss should also sound familiar because we call our Illinois nutrient strategy the Illinois Nutrient Loss Reduction Strategy. That's no coincidence. You've seen this slide before, so I'm going to add to it. Based on the same large-scale study that I mentioned a couple minutes ago, we found the average or the normal kind of rule of thumb tile drainage nitrogen loss is roughly about 20 to 30 kilograms of N per hectare. Converting these units to metric, or converting these metric units into U.S. customary units, we have a mean and a median here of 24 pounds of nitrate nitrogen loss per acre and a median of 19 pounds of nitrate nitrogen loss per acre. So a good rule of thumb here for nitrate loss through tile drains in the Midwest under corn and soybean cropping systems, rule of thumb is about 15 to 30 pounds of nitrogen per acre. That's a rule of thumb for your back pocket. Now, given what you all know about typical nitrogen application rates that we typically apply to corn, I just want to make the point that these levels of nitrogen loss through our tile drains are not insignificant. Now back to our last square. We've talked about water flow and nutrient loads versus losses. How do we actually monitor water that's flowing 3 feet underground? Not only is this water underground, But you might be thinking, well, why don't we just use a flow meter? That makes sense, but the pipes aren't pressurized. We can't use a flow meter because the tile drain pipes are gravity flow rather than pressurized pipes. So how do we do this? Enter one of the most common flow rate measurement methods for water, which uses a stage discharge relationship or a stage discharge equation. Stage is a different way to say water depth or water surface level. Just like I'm showing in the picture, that ruler is helping estimate river stage. Now you'll recognize the word stage because we often talk about flood stage for river. That just means water depth that's resulting in flooding. Flow rates in tile drainage or in streams or in rivers, those flow rates are actually very difficult to measure, especially if you want continuous flow rate measurements. However, stage or water depth is relatively much easier to measure, even continuously. So we develop a stage discharge relationship so that whatever the water depth is for a given stream or a tile drain, that water depth can be related to a flow rate. How do we relate stage or water depth to a flow rate? Enter the next concept, which is a weir. A weir is simply defined as an obstruction that's purposely placed in a channel or in a flow path over which water flows and over which that water can be measured. There are many shapes and sizes of weirs, like this one in the picture, which would be considered a rectangular broad-crusted weir, or this V-shaped weir in this picture here. The way weirs come into play is that you can place a water depth monitoring device behind the weir or upstream of the weir, and then you can relate the depth of water flowing over that weir to a flow rate because your little water sensor is continuously logging that water depth. The idea here is pretty simple. If you have this much water flowing over that weir, it's a relatively much lower flow rate than if you have this much water flowing over your weir. That's the concept. Now you might be wondering, well, how does this look like in a tile drainage application, again, when we have pipes 3 feet underground? This is where our control structures come into play. You've seen these before when I talked about water sampling a couple minutes ago. And these control structures are like little manholes that allow access down to the tile drain. They're not big enough to climb down into, but they're like little access ports. These control structures have what are called stop logs, or sometimes called plates or gates or even drop chutes, I've heard them called, that you can deploy inside the control structure. The real purpose of these control structures is for conservation drainage practices, like the practice of controlled drainage or bioreactors or saturated buffers, but these control structures also offer an important opportunity to use the stop logs to double as a weir, which we can use for water monitoring. The water monitoring device that's placed upstream of the stop logs, or essentially upstream of this weir that we have placed in the control structure, that water monitoring device is generally a pressure transducer or a pressure sensor, which continuously senses and logs how much water is pushing down on it inside that control structure. And then that depth of water that's actually flowing over the top of those stop logs, that can be related to a flow rate. How exactly do we come up with how a water depth in a control structure relates to a flow rate? We calibrate that in the lab. We calibrate these stop log weir plates in a lab. We set up a control structure, like that big gray structure you see. We pump water through it, and then we simultaneously measure water depth flowing through the structure with the water flow rate flowing through that structure. We pump different water flows through the structure, and we get a curve like what you see on the screen, where we can relate water depth above the stop log in inches here with a flow rate through the structure, which here is in gallons per minute. The last thing I'll say about measuring tile drainage flow rates, if you have access to an outlet, which is not always possible, tried and true method is to use a calibrated bucket or a calibrated container where you know the volume and a stopwatch. This only gives you a snapshot of the flow rate at that specific instance in time, but it is actually highly accurate. There is no truer measure of flow rate than a calibrated bucket or container and a stopwatch, because that truly is a volume per time. Now, while this method is highly accurate, it is not very precise. And so that's why you would want to do a couple repeated measurements at any given time to increase your precision and reduce your uncertainty or variability. However, it's a pretty good option if you're just curious for a quick flow rate. Now we're back to the home base. At the very end, we've talked through all four parts of the square. We've talked about the why, the what, the how. So I want to thank you for tuning in today. I hope you've learned a little bit about edge of field tile drainage monitoring. Please stay safe, please stay healthy, and I'll see you next time.